So this is our senior design conference presentation on designing a Formula SA car. I'm Matt Sorensen.
I'm Jacob Deshane.
I'm Sayan Downs.
I'm Jacobs. Okay, so Formula SA is a collegiate design competition put on by the Society of Automotive Engineers, where students design, build, and compete small-scale Formula-style open-wheel race cars. The competition ranges everywhere from engineering design calculations to manufacturing, all the way to theoretical business and marketing presentations. Everything that really encompasses a small-scale OEM manufacturing process from start to finish.
This senior design project builds skills such as practical design, because we have to focus on designing to set up constraints, optimization, as well as manufacturability. It also builds skills in effective communication and documentation. We have to provide documents for the competition as well as our senior design class.
The main goals for Hare Racing 2024 are to design, manufacture, and aerodynamic package, and along with that, the chassis and the suspension as it all interacts with each other fluidly. Other goals for the year were mass reduction in all components, whether it was in scope or out of scope, for our project, meaning the entire car or just the aspects we're working on. Then more specifically within our scope, we were looking at the torque and rigidity of the chassis, power delivery through the suspension handling and the anti-roll devices, and then just creating a cleaner, lighter, more effective ground clear suspension for the system.
So looking at our aerodynamic package, the whole goal of it is to produce downforce. So there's more force applied to your wheels. So that increased normal force will mean you have more grip. And looking at other cars in the competition, their aerodynamic packages consist of a front wing, rear wing, under tray, nose cone, and side pods. All these aerodynamic devices basically work on the principle of accelerating air to create low pressure regions underneath the elements and high pressure regions up top, so it sucks the car down towards the ground.
We began our aerodynamic design with lap time optimization using a program called Optimum Lap. We created a track similar to the one we'll be racing on in Michigan in May. This gave us a downforce and drag coefficient plot where we could kind of figure out where we would be sitting on our lap times. This would guide and help our wing selection as well as our design decisions.
So to make the front and rear wings, we first needed to start with airfoil selection. And up on the slide right now is our method of going about it. So we did a parametric CFD study where we had two main parameters, the position and angle of attacks and different wing elements, as seen up there. And through each one, we can put those input parameters and then run the CFD simulation. So up there is an example of some input parameters that we used on a 3-element wing on that top chart. And then on the bottom is what it outputs. So I have my output parameters selected as force of drag, force of lift, and also the efficiency of the wing elements. So it's how much lift it produces per drag. Main benefit of this is that you can go through hundreds of design points with just putting in your input parameters, and then it'll run through all the calculation and setup and generate useful plots such as like velocity and pressure contours. And then after it does all that, you can go back through your results once you like have it running overnight, and it just really takes the user out of having to babysit the simulations for a long time.
We also designed and simulated under tray designs. This is our best one so far. We're creating a low pressure underneath the car. This helps suck the car to the ground. On the next slide, we can show the plots of our drag and downforce with each under tray. This is our last under tray version. These were all from scratch. And our last under tray is producing about 140 meters of downforce.
After we had our under tray and wings design, we did a full car analysis through CFD. So first we wanted to get a baseline, so we did analysis without any aero devices on it. And that was giving us a coefficient of drag of 0.63 and a coefficient of lift of negative 0.26. So the car was actually, the force was lifting the car up instead of pushing it down. Then we added that Hare package, both the coefficient of drag and coefficient of lift increased. So we're having a lot more downforce with a slight increase of drag. To put it in some more useful numbers, we were generating about 75 pounds of downforce while only creating about 8 pounds of drag from our Hare process.
Going back to our initial design, from the initial testing of the full simulation, we're sitting around that pink dot. This would keep us at lap times of about 155 seconds. Previously, our fastest time last year was 165 seconds for lap time, so that would be 10 seconds faster.
So tires are the only part of the vehicle that's allowed to have contact with the road. And so in order to maximize our grip, we do work with the suspension and aero to optimize our tire contact. If you look at the figure on the right, that is a diagram of slip angle. Slip angle is the change in direction from the actual vehicle path to the direction of the tire. So if your car is going in a straight line, but your tires turn, the contact patch will be aligned with the direction of your vehicle versus the direction of your tire up to a certain point, and that angle is called your slip angle. Figure on the left shows camber. Camber is the inward or outward tilt of your wheels. Most vehicles run a negative camber, which is what is pictured above here. So this picture right here is tire data for slip angle versus normalized lateral force. The figure on the right shows a bunch of different setups for camber, velocity, and tire pressure. Just to look at what setup was the best, the green line, as you can see, maximized our lateral force. And this plot right here is that setup with different normal loads. So the figure on the left is that setup for not normalized forces and just regular lateral force versus slip angle. And that red line right there is they call it the line of peaks. That is where peak lateral force occurs at each different vertical load. And so following that line of peaks, you can see that the max vertical load occurs at a higher slip angle. What this means is that when you're cornering, your load is transferred to your outside tire, and therefore that tire requires a higher slip angle to maximize grip. So if you look at this picture on the right, that shows different steering setups. To maximize grip for this condition of tire, you'll have to run an anti-Ackerman or reverse Ackerman geometry, which is the outer tire turning in more. And this will drive suspension geometry such as caster and camber.
Once you've got aero pushing down, you've got the tires pushing up, you got to do everything. Okay. So starting at the chassis, 2023 car at a torsional rigidity of 660 newton meters per degree. And torsional rigidity is essentially just looking at the frame as a giant torsional spring running along the center axis, the length of the car. And it just affects the load. It's basically how the load transfers side to side to the load. So what that determines. Chassis weight of the 2023 car is also 68 pounds unwelded. So goals for this year were to increase torsional rigidity to a theoretical baseline FSE goal of 2,000 newton meters per degree, which is widely accepted for about the past decade, and also try to reduce weight. Reducing weight while increasing torsional rigidity is hard because a lot of times you're just trying to do that. So I'm really pleased to achieve a torsional rigidity of 2,050 newton meters per degree, while I was able to take 3.5 pounds out of the unwelded frame. The tubes in red are the the tubes that were modified or change in wall thickness or change in length or geometry between the 23 and 24 car. The noticeable differences, while not being able to see the whole frame, there's a lot of X bracing and then utilization of 4 or 5 different wall thicknesses were a lot of use. That colorful picture on the left there is an FEA simulation that I was using as my baseline for the torsional rigidity. Basically, what you're looking at is displacement, with the red being the greatest displacement, and that displacement value is to calculate a basic spring, stiffness. So in the front suspension, once we had the torsion rigidity determined, I was able to use some vehicular dynamics simulators which are essentially just big Excel sheets, to determine different motion ratios and spring rates for the front rear suspension. And using those motion ratios and spring rates, I calculate peak loads through bumps, cornering, and rebounds. And that's how I was able to do FBA simulations or wall thickness simulations for the arms or push rods, for example. For the design solution for the front, they determined a shoulder mounted push rod suspension, which compared to the old overhead push rod suspension, has a lower center of gravity and just lighter overall system weight due to shorter lengths and smaller components. It also cleans up the aerodynamics by pulling a lot of suspension components off the top of the nose cone, and allows us to have a greater camber caster and angle adjustability due to more perpendicular and parallel angles between all of our leads. And then in the rear, we did have to go with the overhead push rod just due to packaging. It's nice to have clearance between all your moving components, being the half shaft there in black, as well as the push rods and anti-roll links all need to have to use each other. So the overhead is what we decided on there. But in order to reduce the center of gravity of the system, we inverted the upright, which is not even in this picture, but actually the upright is now an upside down triangle as opposed to a right side up triangle, which lowers CG. And then to address an issue we've been having in the past with compliance, the compliance is just how much a system's allowed to move under a dynamic situation, and compliance leads to instability and unpredictability. So the toe or control arm that we link there at the bottom, we made independent and then made it as perpendicular to the frame as possible, which gives us the most control and hopefully avoid any instabilities. And there's our overall model. As it says, everything that's within senior design scope is in that overall model, as well as stuff that was out of scope that affected us, like the engine, rims and tires, seat and ergonomics and stuff like that. The overall model is really important to us because it allows us as individual sub teams to interact with each other a lot more as opposed to designing our own individual sub teams and trying to throw them together sections. And another big push this year was mass reduction. So the 2023 car was made into a mass tracker. So on the left here, you can see our total breakdown of mass between all different subsystems, being engine, drivetrain, chassis, suspension, aero, controls, etc. Chassis in green, suspensions in blue, and arrows in yellow. That yellow bar is going to get a lot bigger this year, so we're hoping to reduce the green and blue bars and kind of keep that separation same. And then that's just a component breakdown there on the page.
This was part of our design goals or our Gantt chart. We have a couple of things left to do for the end of semester, but nothing crazy. Next is just our major deadlines for the class. We're just got our critical design review there, and then our competition deadline. Our first competition deadline is in December, and then we compete it next.
So this is the budget for our aero subsystem. It's broken down into a total cost, so what it would cost us if you're starting from scratch, but we already have some of our consumables and materials ordered from previous years, so we also have an adjusted cost. And the difference is around $700. The pie chart on the right is just kind of a component breakdown of each sys or aerodynamic device, and then how much it'll cost to manufacture. Manufacturing is a big part of our expense because there's a lot of consumable materials that go into making our carbon fiber covers.
So this is our frame and suspension budget. As you can see, the initial cost would be roughly $20,500 before we consider donated materials and materials we already have. So our rims and tires are extremely expensive, and then also our frame. So after adjusting for that, our cost estimate for frame and suspension is roughly $3,500, bringing the total cost of the project to $4,500.
Yeah, I like all the detailed testing you guys did on the components, and if you don't mind me asking, could you kind of describe what type of, because you spoke on manufacturability of these parts, what would that look like? How do you want to manufacture these aerodynamic components?
Yeah, so a lot of our components are made out of carbon fiber. So it's a pretty labor intensive process. You have to start off by making a mold. And once you make the mold, you have to do the actual layup, which involves resin. Well, what we do is just a wet resin layup. So you essentially put your carbon fiber down on the mold, you lay up your resin, then you add a layer of Q apply so it does vacuum bag doesn't stick to your resin. Then once you have that, you put your vacuum bag down, you have to make a complete seal and have a tube that basically sucks that hooks up to a vacuum and sucks it down and compresses everything. So it'll pull out excess resin and then just help the shape and form to the mold.
Thanks. You mentioned you had a simulated track time of 150 seconds. Where does that place you on those groups?
So our top 20% was all going below 146 seconds. So it does put us a little lower than our goal. But based on our weights and where the car is at right now, that's probably as best as we can do. Looking at just improving from year to year, but a push to top 20 doesn't seem as long.
Also, that this is still a simulation, so it's not perfectly known. So if we could maybe get a better idea if we ran try to model another competitive car and see what it would spit out.
We swapped engines this year, and so that data that she's basing off of the lab is based off of torque power curves. We're just pulling off the internet right now. Hoping that the data changes, we can actually.
Yeah, there's a lot of factors, and then also for the simulation, we base it off of we got some of our lateral grip and longitudinal grip coefficients from testing with the old car on a more realistic surface. So that could also be a factor as well.
Probably asked this before, but what would be the benefit of having an active aero package versus just having a passive aero package?
So if you had an active aero package, you could decrease your drag going down the straights, and it can be beneficial, but one it would increase complexity, and you're going to have to justify adding in one of the way to have those components so you can have active aero and have those simulations. So it's a lot more extra work, and you're going to have to be able to justify it to the design judges. The other thing, if you kind of look at that track, there's a lot of curved areas and not a ton of straightaway areas on that endurance track. So you could design it, but for this kind of racing, it's a lot more kind of lower speed and cornering, especially because they don't want these cars to be going into super high speed corners just for safety thing.
Yeah.
Does this graph take into weight at all?
Yeah.
It does. This is simulated with our current weight, not our goal weight. So that could decrease that time.
If you add aero, aren't you adding weight? So how does that affect your overall performance?
Right now, our weight goals are to decrease the weight of the rest of the vehicle to accommodate for increased aerodynamic weight. So we'll be sitting pretty even, but it will be included in the aerodynamic weight.
Are all your airfoils carbon fiber, or you guys would use some other covering?
So that's something we're gonna look into. Right now, they're probably gonna be carbon fiber, just because it's very proven and reliable. And if we have time to second semester maybe test some other options, we will. But as of right now, we're gonna probably stick to doing carbon, just because we have most experience with that material and it's most used by other teams, so there's more resources about it.
Any last second questions?
If not, good job.